1995, Michel Mayor and Didier Queloz pointed a spectrograph at a star called 51 Pegasi and watched it wobble. The wobble was subtle, a shift in the star's light spectrum of about 50 meters per second, roughly the speed of a fast cyclist. But that wobble meant something was tugging on the star, something massive, something in orbit. They had found a planet around another sun. 51 Pegasi b was nothing like Earth. It was a bloated gas giant, about half the mass of Jupiter, whipping around its star every 4.2 days in an orbit so tight the surface temperature exceeded 1,000 degrees Celsius. If you could somehow stand on the cloud tops, you would be incinerated instantly. It was a hostile alien world, utterly inhospitable to life as we know it. But it proved something extraordinary. Planets existed beyond our solar system, and if one existed, there had to be more. 3 decades later, we have confirmed over 5,700 of them. Gas giants that orbit their stars in days. Ice giants the size of Uranus. Lava worlds where the surface runs with molten rock. Planets with densities so low they would float on water. Planets so dense they might be made of diamond. Planets with 2 suns in their sky. Planets flung into the void between stars, wandering alone in eternal darkness, heated only by the decay of radioactive elements in their cores. But out of all those thousands of worlds, we keep coming back to one question, the question that launched 100 space missions and consumed tens of billions of dollars and occupied the careers of thousands of scientists across dozens of countries. Is there another Earth out there? A rocky world, the right size, the right temperature, orbiting at the right distance from a stable star. A place where liquid water could pool on the surface and complex chemistry could unfold and maybe, just maybe, something could be alive. We have found candidates, dozens of them. Worlds that appear at first glance to check all the boxes. And every few years, headlines scream that we have finally discovered Earth's twin, the planet that proves we are not alone in the cosmos. But here is what those headlines do not tell you. Almost every promising candidate we have found comes with a devastating asterisk. The planet that scored highest on our Earth Similarity Index gets bombarded with radiation so intense it would sterilize the surface every few months. The one orbiting a sun most like our own might not actually exist. The system with 7 Earth-sized rocky worlds appears to have been scoured of atmospheres by its ancient, angry star. And the world where we thought we detected signs of life, that claim is falling apart under scrutiny as we speak. So what is the most Earth-like planet we have ever found? The answer is more complicated, more fascinating, and more honest than any headline has ever conveyed. And to understand it, we need to start with a fundamental problem that most people never consider. We do not actually know what Earth-like means. When astronomers talk about potentially habitable planets, they are usually talking about 3 things: size, temperature, and location. Size matters because of gravity and composition. A planet needs enough mass to hold onto an atmosphere against the vacuum of space, but not so much mass that it becomes a gas giant. Earth sits in a sweet spot. Our planet has enough gravity to retain nitrogen, oxygen, water vapor, and the other gases that make life possible. But we are not so massive that we crushed ourselves under a suffocating hydrogen and helium envelope, like Jupiter or Saturn or even smaller Neptune. The dividing line between rocky worlds and gas-dominated worlds is not perfectly understood, but observations have revealed a rough threshold. Planets below about 1.6 Earth radii tend to be rocky. Above that size, they increasingly tend to be mini-Neptunes, worlds with thick gaseous envelopes that might lack solid surfaces entirely. This is not an absolute rule. But if you show me a planet with a radius of 2 Earth radii and ask me to bet on its composition, I am betting on gas, not rock. Temperature matters for obvious reasons. Liquid water requires a narrow range of conditions. Below 0 degrees Celsius, at standard pressure, water freezes solid. Above 100 degrees, it boils away. Earth's global average temperature of about 15 degrees Celsius keeps our oceans liquid, and liquid water is essential for every form of life we have ever discovered. That might be a failure of imagination on our part. Maybe life can exist in ammonia seas or methane lakes. But if we are looking for life we know how to recognize, we are looking for liquid water, which means we are looking for temperatures in a specific range. Location determines temperature, at least in the simplest models. The habitable zone, sometimes called the Goldilocks zone in popular articles, is the orbital distance from a star where a planet receives enough energy for liquid water to exist on the surface, but not so much energy that the water boils away. For our Sun, that zone stretches from about 0.95 astronomical units to 1.37 astronomical units. 1 astronomical unit is the distance from Earth to the Sun, about 150 million kilometers. Earth orbits at exactly 1 astronomical unit, comfortably inside the habitable zone. But here is where the concept starts to fall apart, and why you should be suspicious every time someone claims to have found a habitable planet. Venus orbits at 0.72 astronomical units. By some definitions of the habitable zone, that puts it inside the Goldilocks region. And yet, Venus has a surface temperature of 460 degrees Celsius, hot enough to melt lead. Under an atmosphere 90 times denser than Earth's, the pressure at the surface of Venus is equivalent to being a kilometer deep in Earth's ocean. The clouds are made of sulfuric acid. If you dropped a human on Venus, they would be simultaneously crushed, incinerated, and dissolved. Venus is emphatically not habitable despite its location. What went wrong? Venus is only slightly smaller than Earth. It sits in or near the habitable zone. It probably had liquid water early in its history, but something triggered a runaway greenhouse effect. Carbon dioxide accumulated in the atmosphere, trapping heat, evaporating water, which trapped more heat, until the planet became a pressure cooker. Venus might have been habitable for up to 2 billion years before the catastrophe. Now it is hell. Mars tells the opposite story. It orbits at 1.52 astronomical units, squarely in the outer habitable zone by most definitions, and its average surface temperature is negative 60 degrees Celsius, with an atmospheric pressure less than 1% of Earth's. You would suffocate and freeze almost simultaneously. The water that once carved river valleys on the Martian surface is now locked in ice caps and permafrost, or lost entirely to space. What went wrong with Mars? The planet was too small. At only about 10% of Earth's mass, Mars could not hold on to its internal heat. The core cooled. The magnetic field, which is generated by convection in a liquid outer core, died, and without that magnetic shield, The solar wind stripped away the atmosphere molecule by molecule over hundreds of millions of years until almost nothing remained. Mars might have been habitable 4 billion years ago. Today, it is a frozen desert. So, when we say a planet is in the habitable zone, we are not saying it is habitable. We are saying it occupies a region of space where habitability is theoretically possible if a dozen other factors line up correctly. The atmosphere has to be the right composition and pressure. The planet needs a magnetic field to protect against stellar wind. There has to be geological activity to cycle carbon and regulate climate. Water has to actually exist on the surface, not just be theoretically permitted by temperature. The star has to be stable and not produce sterilizing flares. The orbit has to be circular enough to avoid wild temperature swings between closest approach and farthest distance. The habitable zone is not a guarantee. It is a filter, a way to narrow down thousands of candidates to dozens worth studying in detail. And even then, most of those dozens will turn out to be false hopes. The habitable zone is where we start looking. It is not where the search ends. Let me elaborate on why location in the habitable zone is so insufficient, because this point cannot be overstated. For a planet to be truly habitable by Earth-like life, it needs much more than the right temperature at the right distance. It needs an atmosphere of the right composition. Earth's atmosphere is about 78% nitrogen, 21% oxygen, and small amounts of other gases, including water vapor, carbon dioxide, and argon. The nitrogen provides bulk and pressure. The oxygen supports complex metabolism. The carbon dioxide, even at trace levels, provides enough greenhouse warming to keep the planet comfortably above freezing. Water vapor in the atmosphere is essential for the hydrological cycle that distributes water across the surface. Change any of these components significantly, and Earth becomes uninhabitable. Too much carbon dioxide, and we get Venus. Too little, and we get a frozen world. Replace oxygen with something else, and animals cannot breathe. Remove the atmospheric pressure, and water boils away even at low temperatures, just as it does on Mars. Beyond atmosphere, a habitable planet almost certainly needs a magnetic field. Earth generates its magnetic field through convection in the liquid outer core. The core rotates, electrically conductive iron flows in complex patterns, and the result is a dipole magnetic field that extends far into space. This magnetic field deflects the solar wind, a constant stream of charged particles flowing outward from the sun at hundreds of kilometers per second. Without the magnetic field, the solar wind would gradually strip away the atmosphere, molecule by molecule. Mars lost its magnetic field about 4 billion years ago when its small core cooled and solidified. Within a few 100 million years, most of its atmosphere was gone. A habitable planet probably also needs geological activity. Earth's interior is still hot, heated by residual formation energy and radioactive decay. This heat drives plate tectonics, which cycles carbon between the atmosphere and the crust. When carbon dioxide dissolves in rainwater, it forms carbonic acid that weathers rocks. The carbon ends up in the ocean and eventually in sediments. Plate tectonics carries those sediments down into the mantle, where heat releases the carbon as volcanic CO2. This carbon silicate cycle acts as a thermostat, regulating Earth's climate over millions of years. Without it, the climate would drift uncontrollably hot or cold, water has to actually be present, not merely permitted by temperature. A planet in the habitable zone receives the right amount of energy for liquid water, but that does not mean water exists there. Water had to be delivered to the planet during formation, or later by comets and asteroids. If a planet formed too close to its star, water-bearing minerals would never have condensed. If it formed too far out, water might be locked in ice. The delivery of water to rocky planets is chaotic and uncertain. Earth got lucky. We do not know how many planets in habitable zones were not so fortunate. The star itself must be stable. Our sun is remarkably quiet by cosmic standards. It produces solar flares, but they are modest. The solar luminosity varies by only about 0.1% over the 11-year solar cycle. Compare this to red dwarfs that produce superflares 10 times more powerful than any solar flare, or to young stars that vary in brightness by factors of 2 or more. A stable star provides a stable energy budget. An unstable star creates a chaotic environment where atmospheres can be stripped and surfaces sterilized. The orbit must be nearly circular. Earth's orbit is close to circular, with an eccentricity of only 0.017. This means the distance from Earth to the Sun varies by only about 3% over the course of a year, and the energy we receive varies by about 6%. Some exoplanets have highly elliptical orbits that carry them from scorching close to their star to frozen far away. Even if the average temperature is right for liquid water, the temperature swings might be too extreme for life. All of these factors interact. A planet might compensate for a slightly too cold orbit with a thicker greenhouse atmosphere. A strong magnetic field might protect an atmosphere even from a moderately active star. A large moon might stabilize the planet's axial tilt and prevent climate chaos. The presence of life itself might modify the atmosphere and maintain habitability. The point is that the habitable zone is just the beginning. When we find a planet in the habitable zone, we have found a candidate for further study. We have not found a habitable world. Before we examine the candidates, I need to explain how we find these planets in the first place, because understanding the methods reveals why so many discoveries come with asterisks and caveats. We find exoplanets primarily through 2 techniques, and each one tells us only part of the story. The first method is transit photometry. When a planet passes between its star and Earth, it blocks a tiny fraction of the starlight. By measuring how much the light dims and how often the dimming occurs, we can calculate the planet's size relative to its star and its orbital period. The Kepler Space Telescope used this technique to staggering effect between 2009 and 2018. Kepler stared at a single patch of sky containing about 150,000 stars and measured the brightness of each one every 30 minutes. Over 9 years of observations, it detected the characteristic dimming patterns of over 2,700 confirmed planets and thousands more candidates still being analyzed. The Transiting Exoplanet Survey Satellite, TESS, has been doing the same job since 2018, but with a different strategy. Instead of staring at one patch deeply, TESS surveys the entire sky, focusing on bright nearby stars. The planets it finds are close enough for detailed follow-up observations. Transit photometry is remarkably powerful. We can measure planetary radii to within a few percent. We can determine orbital periods with precision. We can even study the composition of atmospheres by analyzing how starlight filters through when the planet is in front of the star. But transit photometry has a critical limitation. It tells us how big a planet is. It does not tell us how massive it is. And without mass, we cannot calculate density. Without density, we cannot know if a planet is rocky like Earth, icy like the moons of Jupiter, or a puffed up ball of hydrogen and helium with no solid surface at all. Think about it this way. A styrofoam ball and a lead ball of identical size would produce identical transit signals. Both block the same amount of light. But one is something you could throw at a friend as a joke, and the other would kill them. Knowing size without knowing mass is like knowing the shadow of an object without knowing anything about the object casting it. The second major method is radial velocity, also called the Doppler technique or the wobble method. Stars with planets are not stationary. The planet's gravity tugs on the star, causing it to wobble slightly around the center of mass of the system. As the star moves toward Earth in its tiny orbit, its light shifts toward the blue end of the spectrum. As it moves away, the light shifts toward the red end. By measuring these minuscule spectral shifts with incredibly precise instruments, we can calculate the planet's gravitational influence and therefore infer its mass. Radial velocity was the technique that found 51 Pegasi b in 1995. It has been refined dramatically since then. Modern spectrographs can detect velocity shifts of less than 1 meter per second, about the walking speed of a person strolling through a park. But radial velocity has its own fundamental limitation. We only measure the component of the stellar wobble along our line of sight. If a planet's orbit is oriented face onto us, the star wobbles side to side and we detect nothing. If the orbit is perfectly edge-on, we see the full wobble. For any angle in between, we only measure a fraction of the true signal. This means radial velocity gives us minimum mass, not true mass. A planet measured at 1 Earth mass might actually be 2 Earth masses or 5 Earth masses if the orbital plane is tilted away from our line of sight. Without knowing the inclination of the orbit, we are stuck with a lower bound on the mass. The gold standard for exoplanet characterization is finding a planet with both methods. If a planet transits its star, we know its orbit is nearly edge-on to our viewpoint. That means the radial velocity measurement gives us close to the true mass, rather than just a minimum. Combine the transit-derived radius with the radial velocity-derived mass, and we can calculate density. Only then can we say with confidence whether a planet is rocky, icy, or gaseous. The problem is that most of our best candidates have only one measurement. The Kepler planets are hundreds or thousands of light years away, too distant for ground-based telescopes to detect their faint stellar wobbles. We know their sizes, but not their masses. The radial velocity planets around nearby stars often do not transit because their orbits are not perfectly aligned with our viewpoint. We know their minimum masses, but not their sizes. This fundamental limitation haunts almost every claim of an Earth-like planet. We are trying to identify twins based on partial information. Imagine trying to find someone's identical twin using only their height or only their weight, but never both. You would get a lot of false matches. There is one more thing to understand. Transit photometry is biased toward finding planets with short orbital periods. A planet that takes a year to orbit its star will only transit once per year. Kepler's 9-year mission could observe at most 9 transits, but confirmation requires multiple transits to establish the pattern. Planets with long orbital periods produce weak signals from limited data. Radial velocity is biased toward finding massive planets on close-in orbits. The bigger the planet and the closer it orbits, the stronger the stellar wobble. Jupiter induces a wobble of about 12 meters per second in our Sun. Earth induces a wobble of just 9 centimeters per second. That is not a typo. 9 centimeters per second. Even our most sensitive instruments can barely detect that. Both methods are biased against finding Earth analogues. An Earth-sized planet on a year-long orbit around a Sun-like star produces a tiny transit signal, a small radial velocity signal, and only one observation per year. These are the hardest planets to find and confirm, which means the Earth-like planets we have found are not necessarily the most common. They are the ones that happen to be findable with current technology. Let me take you through the candidates now, starting with the ones that made the biggest headlines and working toward the one that currently deserves the title of most Earth-like. Along the way, you will see how each discovery revealed new truths about the search for another Earth, including truths we did not want to hear. In July of 2015, NASA held a press conference to announce the discovery of Kepler 452b. The media coverage was rapturous. NASA called it Earth's bigger, older cousin. Some outlets dropped the qualifiers entirely and called it Earth 2.0. On paper, Kepler 452b looked extraordinary. It orbited a star almost identical to our Sun, a G-type main sequence star only 6% more luminous than the Sun and about 1.5 billion years older. The planet completed one orbit every 385 days, almost exactly like Earth's 365-day year. It sat squarely in the habitable zone, receiving about 10% more energy than Earth receives from the Sun. This was the first time anyone had found a planet in the habitable zone of a Sun-like star with a near-Earth orbital period. Every previous habitable zone candidate orbited red dwarf stars or had much shorter or longer orbital periods. Kepler 452b seemed to be the real deal. But even at the time of the announcement, there were problems. Kepler 452b has a radius of roughly 1.6 Earth radii. That number might sound small, but it puts the planet right at a critical threshold identified by astronomer Leslie Rogers in 2015. Rogers analyzed the masses and radii of known exoplanets and found a transition point. Below about 1.6 Earth radii, planets tend to be rocky. Above that threshold, they increasingly tend to have thick hydrogen and helium envelopes, making them more like small Neptunes than large Earths. Kepler 452b sits exactly on the boundary. Its rocky nature is a coin flip at best. Statistical estimates put the probability of a rocky composition somewhere between 49 and 62%. That is not terrible odds, but it is not a confident identification either. Far more troubling was the distance. Kepler 452b orbits approximately 1,400 light-years away. At that distance, the transit signal is faint, and the star is too dim for follow-up radial velocity measurements with current instruments. We have no mass measurement for this planet. We do not know if it is rocky or a gas ball. We are guessing. And then came the statistical analysis that really undermined the discovery. In 2018, researchers led by Fergal Mullally re-examined Kepler's long-period planet candidates using rigorous false positive probability calculations. The problem with Kepler is that many things can mimic a planetary transit. Background eclipsing binary stars, instrumental artifacts, stellar variability. For short-period planets with many observed transits, these false positives can be identified and rejected. For long-period planets with only a handful of transits over Kepler's lifetime, distinguishing real planets from noise is much harder. Mullally's team found that for low signal-to-noise, long-period candidates like Kepler 452b, the statistical validation had a reliability of only about 16%. That is not a discovery. That is a suggestion, a hint, a maybe. The following year, Christopher Burke and colleagues reached similar conclusions using different methods. The planet's existence remained unconfirmed. NASA's own Exoplanet Archive now lists Kepler 452n with a controversial flag. The entry notes that independent analyses have questioned the detection. The planet that was supposed to be Earth's twin might not exist at all. This is not a failure of the Kepler mission. Kepler was designed to answer a statistical question: how common are Earth-like planets? It answered that question magnificently, but confirming individual long-period planets around distant, dim stars was never part of the mission's core capability. Kepler told us that planets like Kepler 452b should be common throughout the galaxy. Whether this specific one is real remains uncertain. If Kepler 452b disappointed because it might not exist, the next great hope disappointed for the opposite reason. Kepler 438b definitely exists. It just cannot support life. Announced in January of 2015, Kepler 438b achieved the highest Earth Similarity Index ever recorded at the time, 0.888 out of a maximum score of 1.0. For context, Mars scores about 0.70. Kepler 438b was apparently more Earth-like than any planet we had ever found. On paper, the discovery looked perfect. The planet has a radius of 1.12 Earth radii, firmly in the rocky category, with none of the compositional ambiguity of Kepler 452b. It orbits in the habitable zone of its host star. Models suggested a surface temperature around 3 degrees Celsius, chilly but potentially comfortable with the right atmosphere. For a few months, Kepler 438b was the crown jewel of exoplanet discoveries, the closest thing to Earth anyone had ever seen. Then, in November of 2015, a team from the University of Warwick in England published devastating news. They had been studying the host star, Kepler 438, and they found something disturbing. Kepler 438 is a red dwarf star, an M-type star much smaller and cooler than our Sun. Red dwarfs are the most common type of star in the galaxy. They make up about 70 to 80% of all stars. Their habitable zones sit close in because they produce less energy than Sun-like stars. A planet in the habitable zone of a red dwarf might complete an orbit in just days or weeks rather than months or years. But red dwarfs have a problem. Many of them are magnetically active. They produce flares, not ordinary solar flares. Our Sun produces flares too, and Earth handles them fine because we have a magnetic field and we orbit at a comfortable distance. The flares from Kepler 438 are superflares. events 10 times more powerful than any flare ever recorded from our sun. And they happen every 100 days or so. Each superflare bathes Kepler 438b in radiation intense enough to strip away any atmosphere the planet might have. Without an atmosphere, there is no pressure to keep liquid water on the surface. Water would sublime directly from ice to vapor and escape into space. Without liquid water, the kind of chemistry that leads to life cannot occur. The Warwick researchers did not just identify the problem, they quantified it. Their models showed that the superflares were stripping Kepler 438b of atmosphere at a rate that would devastate any Earth-like environment. Even with a magnetic field, which we do not know the planet has, the radiation environment would be punishing. The team's lead author, David Armstrong, was blunt in interviews. Despite its high Earth Similarity Index, Kepler 438b is almost certainly not habitable. This revealed a fundamental flaw in how we rank Earth-like planets. The Earth Similarity Index considers size, density, escape velocity, and surface temperature. It does not consider the star, and the star matters enormously. Let me pause here to address why so many of our best candidates orbit red dwarf stars, and why that is a problem. Red dwarfs are attractive targets for planet hunters for purely practical reasons. Their habitable zones are close in, which means planets there orbit quickly and produce many transits per year. Their small size means planets block a larger fraction of their light, producing stronger transit signals. Their low luminosity means the contrast between star and planet is smaller, making direct imaging and atmospheric characterization easier. When we survey nearby stars for habitable zone planets, we inevitably find them around red dwarfs because red dwarfs make finding them easy. This is a selection bias. We find what we can find, not necessarily what is most common or most promising. But red dwarfs present serious challenges for habitability. The first problem is tidal locking. Because habitable zone planets orbit so close to their red dwarf hosts, gravitational forces slow the planet's rotation until one hemisphere permanently faces the star. This is the same phenomenon that keeps the same side of the Moon always facing Earth. On a tidally locked planet, one hemisphere experiences eternal day, while the other experiences eternal night. The temperature difference between the two sides could be extreme. The day side might bake at hundreds of degrees, while the night side freezes at hundreds of degrees below zero. Whether an atmosphere can redistribute heat effectively between hemispheres is still debated. Some models suggest atmospheric circulation could moderate temperatures. Others suggest the atmosphere itself might freeze out on the dark side. The second problem is stellar flares. Young red dwarfs are extremely active magnetically. They produce frequent, powerful flares that bombard close-in planets with X-rays, ultraviolet radiation, and charged particles. Even older red dwarfs can remain active. Kepler 438 is about 4 billion years old, comparable to our Sun, and it still produces super flares every few months. Flares damage atmospheres through multiple mechanisms. Direct radiation heats the upper atmosphere, causing it to expand and escape into space. Charged particles strip away molecules directly. Ultraviolet light breaks apart molecules like water and ozone. Over billions of years, even a thick initial atmosphere could be completely stripped away. The third problem is the pre-main sequence phase. Before settling into stable hydrogen fusion, red dwarfs spend tens of millions to hundreds of millions of years in a swollen, luminous state. During this phase, they can be 100 times brighter than their eventual stable luminosity. Planets that currently sit in the habitable zone would have been scorched during this early period. Consider what this means for a planet forming around a red dwarf. For the first 100 million years or more, the planet is roasted by a star far brighter than it will eventually become. Any water delivered during planetary formation evaporates into space. Any primordial atmosphere is baked away. By the time the star settles down and the habitable zone moves inward to encompass the planet's orbit, the planet has already been sterilized. Some researchers argue that water and atmosphere could be replenished later by comet impacts or volcanic outgassing. Others argue the damage is irreversible. This remains one of the great uncertainties in exoplanet habitability. The pattern we see is clear. Red dwarfs offer the best opportunities for detection, but they may offer the worst conditions for life. The planets we find most easily might be the ones least likely to be habitable. Before we continue to the next candidates, I want to put the distances involved into perspective. Because the numbers are so large, they lose meaning without context. This is perhaps the most important section of this entire video, because without grasping the scale, nothing else makes sense. A light year is the distance light travels in 1 year. Light moves at roughly 300,000 kilometers per second. That is fast enough to circle Earth 7.5 times in a single second. In 1 year, light covers about 9.5 trillion kilometers. Write that number out, and it has 13 digits. It is incomprehensibly large. Kepler 452b, if it exists, is approximately 1,400 light years from Earth. Multiply 9.5 trillion by 1,400, and you get a number so large that writing it serves no purpose. Instead, think about it in terms of time. The light we see from Kepler 452b star today left around the year 626 CE. Muhammad had not yet begun receiving the revelations that would become the Quran. The Roman Empire in the West had been gone for 150 years. The Byzantine Empire was fighting for survival against Persia. The Tang dynasty was consolidating control over China. Anglo-Saxon kingdoms were slowly converting to Christianity. Nothing we would recognize as modern civilization existed anywhere on Earth. Everything that has happened since then, the entire medieval period, the Renaissance, the scientific revolution, the Enlightenment, the Industrial Revolution, 2 world wars, the space age, the internet, all of that occurred while photons were making their way from that star to our telescopes. Kepler 438b is about 470 light years away. The light we see today left during the reign of Queen Elizabeth I, as Shakespeare was writing his plays and Galileo was turning his telescope toward the heavens. TRAPPIST-1 is 40 light years away. The light we observe tonight left in 1986 as the Challenger disaster shocked the world and the Chernobyl reactor melted down. Proxima Centauri, the closest star system, is 4.24 light years away. Light from Proxima Centauri that reaches us today left in late 2021 or early 2022. These are the distances we are dealing with, and light speed is the absolute cosmic speed limit. Nothing with mass can reach it. Nothing we can build will ever travel that fast. So let me make the distances concrete in terms of actual travel. The fastest object humanity has ever built is the Parker Solar Probe, a NASA spacecraft designed to study the Sun at close range. During its closest approaches to the Sun, it reaches speeds of about 170 kilometers per second. That is impossibly fast by any human standard. At that speed, you could travel from New York to Los Angeles in about 15 seconds. But space is vast. At Parker Solar Probe speeds, reaching Proxima Centauri would take approximately 7,500 years. That is longer than recorded human history. That is almost as long as humans have practiced agriculture. You would leave Earth as the pyramids were being built and arrive around now. Reaching TRAPPIST-1 at Parker Solar Probe speeds would take about 70,000 years. Modern humans have only existed for about 300,000 years. 70,000 years ago, our ancestors were just beginning to migrate out of Africa. You would leave as anatomically modern humans, and by the time you arrived, your descendants would have evolved into something different. Reaching Kepler 452b would take roughly 2.5 million years. That is longer than the entire existence of the genus Homo. You would leave when our ancestors were still Australopithecus, small-brained hominids, barely distinguishable from apes. Let me try another comparison. Voyager 1, launched in 1977, is the most distant human-made object. It has left the solar system and is traveling through interstellar space at about 17 kilometers per second. That is much slower than Parker Solar Probe. At Voyager speeds, reaching Proxima Centauri would take 73,000 to 77,000 years. When Voyager arrived, our descendants would have evolved as much from us as we have evolved from the last common ancestor we shared with chimpanzees. Reaching TRAPPIST-1 would take about 700,000 years. That is longer than Homo sapiens has existed as a species. Reaching Kepler 452b would take approximately 26 to 30 million years. That is longer than the existence of great apes. That is approaching the age of the dinosaurs. These are not travel times we can conceptualize. These are geological timescales, evolutionary timescales. The entire rise and fall of human civilization would fit into a rounding error. But let me try one more approach to make the scale tangible. Forget time. Think about space itself. If you built a scale model where the Sun was a basketball, Earth would be a small bead about 2 millimeters in diameter, orbiting 25 meters away. The edge of the solar system, where the Oort cloud begins, would be about 2,500 kilometers away in this model. The basketball is in your living room, and the edge of the solar system is farther than from London to Moscow. In this same model, Proxima Centauri would be another basketball about 40,000 kilometers away. That is the circumference of the actual Earth. To travel from your living room basketball to the nearest other basketball, you would have to circle the entire real planet. TRAPPIST-1 in this model would be about 400,000 kilometers away. That is the distance from the real Earth to the real Moon. Kepler 452 would be about 14 million kilometers away in this scale model. That is about a tenth of the real distance from Earth to the Sun. When someone casually says a planet is 1,400 light years away, this is what they mean. In a model where the Sun fits in your hand, the planet is farther away than real spacecraft have ever traveled from Earth. These are not distances we will cross, not in our lifetimes, probably not ever. We observe these worlds by collecting photons that have traveled for years or centuries. We infer their properties from shadows and wobbles. We will never visit them. We will never send probes. We will never see close-up images. When we talk about finding Earth-like planets, we are talking about finding them across gulfs so vast that visiting them is not science fiction. It is fantasy. Understanding them from here, across the void, using nothing but light that has traveled longer than civilizations endure, that is the challenge. That is the science. Now let me make this concrete. The fastest object humanity has ever built is the Parker Solar Probe, which reaches speeds around 170 kilometers per second during close passes to the Sun. At that speed, reaching Kepler 438b would take approximately 800,000 years. Reaching Kepler 452 would take about 2.5 million years. Voyager 1, our most distant spacecraft, travels at about 17 kilometers per second. At that speed, reaching Kepler 438b would take roughly 8 million years. Reaching Kepler 452b would take about 26 million years. That is longer than humans have existed as a species. That is longer than the entire lineage leading to modern humans. These are not destinations. These are observations. We will never visit these worlds. We will never send probes. We study them by catching the photons that have traveled for centuries to reach us, analyzing their subtle variations, inferring what we can from shadows and wobbles. When someone asks whether we have found another Earth, they often imagine we could someday visit. The answer is almost certainly no. What we are searching for is something more abstract and perhaps more profound. Evidence that worlds like ours exist, even if we can never touch them. The turning point in exoplanet science came with the discovery of planets around nearby stars, close enough that we could measure both size and mass, close enough that next-generation telescopes could study their atmospheres, close enough that just maybe we might learn something definitive. In August of 2016, astronomers announced the detection of Proxima Centauri b, not Proxima Centauri 186 or 452b, just b, the first confirmed planet orbiting the closest star to our Sun. Proxima Centauri is part of the Alpha Centauri system, the nearest star system to Earth at just 4.24 light-years away. In astronomical terms, that is practically next door. The light we see from Proxima Centauri left in early 2022. If we ever develop interstellar travel, this would likely be the first destination. The planet was found using the radial velocity method. Proxima Centauri wobbles back and forth with a period of 11.2 days, revealing a planet with a minimum mass of 1.07 Earth masses. That minimum mass is almost identical to our own planet. Even accounting for reasonable orbital inclinations, the planet is probably less than 2 or 3 Earth masses. It orbits within the habitable zone of its dim red star, receiving about 65% of the energy Earth receives from the Sun. For a moment, it seemed too good to be true. A roughly Earth mass planet in the habitable zone of the nearest star system. Headlines proclaimed, "We had found a potentially habitable world in our cosmic backyard." The distance to Proxima Centauri deserves its own treatment because it represents a meaningful target for speculation about interstellar travel. At 4.24 light-years, Proxima Centauri is 40 trillion kilometers away. Voyager 1, traveling at 17 kilometers per second, would take about 73,000 years to cover that distance. When it arrived, our descendants would have evolved as much from us as we have from the last common ancestor we shared with chimpanzees. The most ambitious proposed interstellar mission is Breakthrough Starshot, funded by Russian billionaire Yuri Milner. The concept uses powerful ground-based lasers to accelerate gram-scale spacecraft to about 20% of light speed. At that velocity, the journey to Proxima Centauri would take approximately 20 years. The spacecraft would arrive traveling at 60,000 kilometers per second, far too fast to break into orbit. They would fly past, capturing a few seconds of data, and continue into interstellar space forever. Even this ambitious project remains in the study phase. The lasers required do not exist. The spacecraft do not exist. The technology to transmit data back across 4 light-years from a gram-scale probe does not exist. This is not engineering. This is aspiration. But Proxima Centauri B's proximity makes it the most studied exoplanet in terms of what interstellar travel might someday mean. And that study has revealed serious problems. Proxima Centauri is a red dwarf star, and not just any red dwarf. It is one of the most magnetically active stars in the solar neighborhood. In May of 2019, astronomers observed a superflare that increased the star's brightness by a factor of 14,000 in ultraviolet light. For roughly 10 seconds, the star became 10 times brighter than normal across all wavelengths. These flares are not rare. They happen multiple times per year. Proxima Centauri b receives about 30 times more extreme ultraviolet radiation than Earth receives from the Sun. It receives about 250 times more X-rays. Each major flare bombards the planet with radiation that would sterilize any exposed surface and accelerate atmospheric loss. Models suggest that any Earth-like atmosphere around Proxima Centauri b would be destroyed within a few 100 million years of exposure to this radiation environment. The planet might have had an atmosphere once. It almost certainly does not now. We do not have direct measurements to confirm this. The planet does not transit its star from our viewpoint, so we cannot use transmission spectroscopy to study its atmosphere. We know its minimum mass and its orbital period. Everything else is inference and modeling. The closest exoplanet to Earth is probably a radiation-blasted rock with no atmosphere, no water, and no chance of life as we know it. Proximity does not equal habitability. Now we come to the system that captured the world's imagination like no other. The system that seemed, for a shining moment, to offer everything we were looking for. TRAPPIST-1. In February of 2017, NASA held a press conference to announce a remarkable discovery. A team led by Michael Gillen had found 7 Earth-sized planets orbiting a single star just 40 light-years away. 3 of them sat in the habitable zone. All 7 were close enough to each other that standing on one, you could see the others in the sky, some appearing larger than our moon appears from Earth. The discovery was made with the Transiting Planets and Planetesimals Small Telescope, or TRAPPIST, a 60-centimeter robotic telescope located in Chile. The star, initially designated 2MASSJ2306928-0502285, was renamed TRAPPIST-1 after the telescope that revealed its planetary system. The name is fitting in another way too. The TRAPPIST telescope was named after the Trappist order of monks, and the research team, based in Belgium, chose the name partly as a nod to the famous Trappist beers brewed in Belgian monasteries. Astronomy has a tradition of whimsical naming, and TRAPPIST-1 has become one of the most famous star systems discovered in recent decades. TRAPPIST. One itself is tiny by stellar standards. It is an ultra-cool M-dwarf, the smallest and coolest type of star capable of stable hydrogen fusion. Its surface temperature is only about 2500 Kelvin, less than half the temperature of our Sun, is only about 9% of the Sun's mass and about 12% of the Sun's radius. If TRAPPIST-1 replaced our Sun, the star would appear about the same angular size as our Sun appears to us, but it would shine with a dim reddish light. Noon on Earth would look darker than twilight, and the light would have an eerie red tint. To get the same amount of energy that Earth receives from the Sun, a planet would have to orbit TRAPPIST-1 at about 2.4% of the Earth-Sun distance. That is closer than Mercury orbits our Sun. Much closer, because the star is so faint. The habitable zone sits extremely close. All 7 planets orbit within what would be Mercury's distance from our Sun. To visualize the system, imagine squeezing 7 planetary orbits into a space smaller than the orbit of Mercury. The planets are packed so tightly that gravitational interactions between them are significant. The innermost planet, TRAPPIST-1b, completes an orbit in just 1.5 days. It whips around its star so fast that a year lasts less time than a long weekend on Earth. The outermost planet, TRAPPIST-1h, takes about 19 days to complete an orbit. That is still faster than the Moon orbits Earth. The entire system operates on timescales that would seem frantic by solar system standards. The spacing between planets is remarkable. TRAPPIST-1, E, and F, 2 of the habitable zone candidates, are separated by only about 1 million kilometers. For comparison, Venus and Earth never come closer than about 40 million kilometers. Standing on TRAPPIST-1e, you could see TRAPPIST-1f in the sky, appearing about twice the diameter of our full moon. During close approaches, you could see surface features with the naked eye if both planets have surfaces. This tight configuration is what allowed such precise measurements. The planets are close enough to gravitationally perturb each other in measurable ways. It is an ultra-cool M-dwarf with a surface temperature of only about 2500 Kelvin, less than half the temperature of our Sun. It is only about 9% of the Sun's mass and about 12% of the Sun's radius. If you replaced our Sun with TRAPPIST-1, noon on Earth would look darker than twilight. Because the star is so faint, the habitable zone sits extremely close. All 7 planets orbit within the equivalent of Mercury's distance from our Sun. The innermost planet completes an orbit in just 1.5 days. Even the outermost takes only about 19 days. The entire system would fit comfortably inside Mercury's orbit with room to spare. What made TRAPPIST-1 special, what elevated it above every previous discovery, was the quality of the data. All 7 planets transit the star. Because the star is so small, the transit signals are proportionally large, and because the planets orbit so close together, their gravitational interactions create measurable variations in their transit timing. By carefully tracking these timing variations, astronomers calculated the masses of all 7 planets with remarkable precision, typically 3 to 5% uncertainty. This is the gold standard we have been chasing since the beginning. Both mass and radius measured for every planet in the system. No guessing about composition. No uncertainty about whether they are rocky or gaseous. The results were stunning. All 7 planets have densities consistent with rocky compositions. They are all slightly less dense than Earth, suggesting iron-depleted interiors, but none show evidence of thick gaseous envelopes. These are genuine rocky worlds, not mini Neptunes in disguise, not ambiguous boundary cases, rocky planets confirmed. TRAPPIST-1e quickly emerged as the most promising candidate in the system. It is 0.92 Earth radii, slightly smaller than our planet. Its mass is 0.69 Earth masses, about 2/3 our planet's mass. It orbits in the middle of the conservative habitable zone, receiving about the same amount of energy from TRAPPIST-1 that Earth receives from the Sun. Its equilibrium temperature is around 250 Kelvin, negative 23 degrees Celsius. Cold, but potentially temperate with a greenhouse atmosphere. For years, TRAPPIST-1 dominated discussions of potentially habitable exoplanets. Here was a system we could actually study. The star was close enough, and the planets were large enough relative to their star that detailed atmospheric characterization seemed within reach. When the James Webb Space Telescope launched in December of 2021, TRAPPIST-1 was near the top of everyone's observation priority list. The astronomical community held its breath. After decades of finding candidates with asterisks, here was a system that might finally deliver answers. Real data about real atmospheres on real rocky planets in the habitable zone. And then, the James Webb Space Telescope began delivering its verdict. The first JWST observations of TRAPPIST-1 planets targeted TRAPPIST-1b, the innermost world. This was not a habitable zone planet. It orbits so close to its star that surface temperatures were expected to exceed 400 Kelvin, far too hot for liquid water. But it served as a test case. If this scorching world showed evidence of an atmosphere, there was hope for the cooler outer planets. If even this planet had been stripped bare, it boded poorly for the entire system. The results, published in 2023, were crushing. JWST measured the thermal emission from TRAPPIST-1b's dayside, the hemisphere facing the star. The temperature matched predictions for a bare rock with no significant atmosphere. The surface was essentially a dark, airless expanse, heated directly by starlight, with no atmospheric insulation or redistribution of heat. A thick atmosphere would have shown different signatures. Heat would be redistributed to the night side. The effective temperature would differ from pure radiative equilibrium. None of these signatures were present. TRAPPIST-1b is almost certainly a bare rock. Later in 2023, JWST observed TRAPPIST-1c, the second planet. Same result. No thick carbon dioxide atmosphere detected. The dayside temperature matched predictions for an airless or nearly airless world. A paper published in Nature reported that even a pure CO2 atmosphere comparable to Venus's could be ruled out. These results aligned with fears that had been growing for years. TRAPPIST-1 is an old star. Current estimates place its age somewhere between 7 and 8 billion years, making it older than our Sun. And like all M-dwarfs, it spent its youth much more luminous than it is today. Before settling into stable hydrogen fusion, red dwarfs go through a pre-main sequence phase lasting tens of millions to hundreds of millions of years. During this phase, they are swollen and bright. TRAPPIST-1 was probably hundreds of times brighter during its first 100 million years than it is now. Any planets that formed with water or primordial atmospheres would have been baked during this early phase. Oceans would have evaporated, atmospheres would have escaped into space. Then came the flares. TRAPPIST-1 produces about 42 flares per 80 days of observation. Each one blasts the close-in planets with ultraviolet radiation and charged particles. Over billions of years, even atmospheres that survived the initial baking might have been stripped away, molecule by molecule. The JWST observations of TRAPPIST-1b and c appear to confirm this scenario. The inner planets are dead worlds, cooked in their youth and sterilized over billions of years. But what about the habitable zone? What about TRAPPIST-1, E, F, and G? JWST observations of TRAPPIST-1e were conducted in 2024 and 25. The initial data showed a possible hint of methane absorption. Methane is intriguing because it can be produced by biological processes, though it can also be produced geologically. The detection sparked a flicker of hope that TRAPPIST-1e might have retained an atmosphere despite the hostile stellar environment. Subsequent analysis tempered that hope. The potential methane signal might have been caused by stellar contamination, a phenomenon where features in the star's light spectrum create artifacts that mimic atmospheric absorption. When you are looking for signals at the parts per million level, even tiny stellar features can create false positives. The JWST team was able to rule out certain atmospheric compositions. Venus-like atmospheres and Mars-like atmospheres are inconsistent with the data, but they could not confirm any atmosphere at all. TRAPPIST-1e remains in limbo, neither confirmed to have air nor confirmed to be airless. More observations are planned. Over 130 additional hours of JWST observing time have been approved for TRAPPIST-1e. Scientists are not giving up on this system, but the early returns suggest that even the most celebrated candidates may be airless rocks, scoured clean by billions of years of stellar abuse. In late 2024, a new analysis suggested that TRAPPIST-1b might after all have a thin atmosphere, perhaps replenished by volcanic outgassing. The debate continues, but thin volcanic atmospheres are a far cry from the thick, water-rich atmospheres required for surface habitability. The TRAPPIST-1 system taught us something important, something we perhaps should have anticipated but hoped to avoid. Finding rocky planets in the habitable zone is not enough. The star matters. The history matters. A planet that looks perfect today might have lost its habitability billions of years ago, during an era we cannot observe directly. While TRAPPIST-1 was delivering disappointing news from one direction, another candidate was generating headlines for an entirely different reason. K2-18b. This planet orbits a red dwarf star, 124 light-years away. It was discovered in 2015 by the K2 mission. The second phase of Kepler's observations after a reaction wheel failure forced a new observing strategy. At 2.6 Earth radii and 8.6 Earth masses, K2-18b is much larger than Earth. This puts it in the category astronomers call sub-Neptunes, worlds intermediate between rocky planets like Earth and ice giants like Neptune. For years, K2-18b was considered interesting, but not particularly Earth-like. Its size suggested it might have a thick hydrogen envelope, making it more like a small Neptune than a large Earth. Any surface, if one existed, would be buried under crushing layers of gas at pressures and temperatures incompatible with life as we know it. But some researchers proposed an alternative model. What if K2-18b was what they called a Haitian world? The term combines hydrogen and ocean. The idea is a planet with a hydrogen-rich atmosphere overlying a global water ocean. Such a world would be unlike anything in our solar system, but the physics works out. Hydrogen is excellent at retaining heat, so even a relatively small amount could maintain temperate surface conditions. If the atmosphere is not too thick and the ocean is not too hot, life might conceivably exist. The Haitian hypothesis elevated K2-18b from a curiosity to a priority target for JWST. In September of 2023, JWST observed K2-18b and detected molecules in its atmosphere. The detection was unambiguous. Methane was present at 5 sigma confidence, a rock-solid detection. Carbon dioxide was present at 3 sigma, strong, but not quite definitive. Critically, ammonia was detected at low levels, which is consistent with the Haitian model. A thick hydrogen atmosphere would be expected to show abundant ammonia. A hydrogen atmosphere over a water ocean would show less because ammonia dissolves readily in water. The astronomical community was excited but measured. The observations were consistent with an ocean world. They were also consistent with a mini Neptune with no surface at all. More data was needed. Then the research team led by Niku Madhusudan made an additional claim that ignited global headlines. They reported a tentative detection of dimethyl sulfide, or DMS. On Earth, dimethyl sulfide is produced almost exclusively by marine phytoplankton. Tiny ocean organisms release it as a byproduct of their metabolism. It is a genuine biosignature, a molecule strongly associated with life. Detecting DMS on another world would be extraordinary. When news of the possible detection reached the media, the coverage was breathless. Signs of life on an exoplanet, a biosignature on an ocean world. After decades of searching, had we finally found evidence that we are not alone? I need to be very clear about what happened next, because the media coverage badly distorted the science. The initial DMS detection was marginal. The statistical significance was around 2 sigma, meaning there was roughly a 5% chance the signal was just noise. In physics and astronomy, the standard threshold for claiming a discovery is 5 sigma, which corresponds to about a 1 in 3 million chance of a false positive. 2 sigma is not a detection. It is a hint, a suggestion that something might be there and warrants further investigation. By early 2025, Madhusudan's team claimed the detection had strengthened to 3 sigma with additional data. 3 sigma is more interesting, roughly a 1 in 300 chance of being wrong. But it is still not discovery-level confidence, and it was based on the same team's analysis of the same data using the same methods. Independent reanalyses told a different story. In July of 2025, a NASA-led team published their own examination of the K2-18b data. They found no conclusive evidence for DMS. Their analysis showed the signal at only 2.7 sigma. They also demonstrated that the apparent detection was highly sensitive to choices made in the data processing pipeline. Small changes in how the data was reduced, how stellar contamination was modeled, how instrumental artifacts were removed, could make the signal appear or disappear. In August of 2025, another team published an even more comprehensive critique in the journal Astronomy and Astrophysics. They reanalyzed the full dataset using multiple independent methods and found that 87.5% of their analyses showed no statistically significant DMS detection. The signal that Madhusudan's team reported was not robust. It appeared in some analysis pipelines and not others. The most likely explanation, they concluded, was red noise, a type of correlated noise that can mimic real spectral features. There are also theoretical reasons for skepticism. For the DMS detection to be real, K218b would need to produce dimethyl sulfide at rates approximately 20 times higher than Earth's entire biosphere. That is a lot of phytoplankton, or whatever alien equivalent might exist. It is not impossible, but it requires extraordinary biological productivity on a world we know almost nothing about. Furthermore, DMS is not uniquely biological. The Rosetta mission detected it on Comet 67P, where no biology exists. It has been found in interstellar gas clouds. Laboratory experiments published in 2024 demonstrated that DMS can be produced through purely photochemical processes, sunlight-driving reactions in atmospheric gases without any life involved. NASA's official position, carefully worded but clear, is that detection of a single potential biosignature would not constitute discovery of life. Multiple converging lines of evidence would be required. K218b remains a fascinating planet. The confirmed detection of methane and carbon dioxide proves it has a substantial atmosphere amenable to detailed study. Whether that atmosphere overlies a water ocean or just layers of supercritical hydrogen is unknown. Whether anything swims in that hypothetical ocean is pure speculation. The biosignature claim is not confirmed. It is not even a strong hint by the standards of rigorous science. It is a marginal signal that most independent analyses cannot reproduce. That might change with more observations. Or the signal might fade entirely, joining the long list of almost discoveries that seemed promising until better data arrived. Now I want to tell you about the planet that currently has the strongest claim to the title of most Earth-like world we have ever found. It is not the one with the highest Earth Similarity Index. It is not the one that made the most dramatic headlines. It is a planet that most people outside the astronomical community have never heard of. LHS 1140b. The planet was discovered in 2017, orbiting a red dwarf star 49 light-years from Earth. At 1.73 Earth radii and 5.6 Earth masses, it is a super-Earth, significantly larger and more massive than our planet, but still firmly in the rocky regime. It orbits in the habitable zone of its star with a period of about 25 days. For years, LHS 1140b was just one candidate among many. It appeared on lists of potentially habitable planets without particular distinction. Its relatively large size, straddling the boundary between rocky and mini-Neptune, made its composition uncertain. What changed everything was a James Webb Space Telescope observation conducted in December of 2023. The JWST data allowed researchers to pin down the planet's composition far more precisely than before. The results ruled out a mini-Neptune composition at more than 10 sigma confidence. This planet is not a gas-dominated world. It is definitively solid. But the analysis went further. The mass and radius of LHS 1140b are consistent with two possible compositions. It could be a rocky world with an extended atmosphere, or it could be a water world, a planet where between 9 and 19% of the total mass is water. For comparison, Earth is only about 0.02% water by mass. If the water world interpretation is correct, LHS 1140b is covered by a global ocean potentially tens or hundreds of kilometers deep. But the most significant finding was atmospheric. The JWST data showed tentative evidence of a nitrogen-rich atmosphere surrounding LHS 1140b. Nitrogen is the dominant component of Earth's atmosphere, making up about 78% of the air we breathe. It is relatively stable against atmospheric escape, especially compared to lighter gases like hydrogen. Detecting nitrogen on a rocky planet in the habitable zone would be the first confirmation of what astronomers call a secondary atmosphere. Let me explain why that matters. Planets can have two kinds of atmospheres. Primordial atmospheres are captured from the protoplanetary disk during formation and consist primarily of hydrogen and helium, the lightest and most common elements in the universe. Secondary atmospheres form later through geological processes, volcanic outgassing, comet impacts, and other sources. Earth's atmosphere is secondary. Our primordial hydrogen and helium escaped into space billions of years ago, replaced by the nitrogen, oxygen, water vapor, and carbon dioxide that define our current atmosphere. No one has ever confirmed a secondary atmosphere on a potentially habitable exoplanet. The TRAPPIST-1 planets show no clear atmospheres at all. The atmosphere of K218b might be primordial hydrogen. Detecting nitrogen on LHS 1140b would be genuinely groundbreaking. But I must be careful here. The detection is tentative. The statistical significance is only about 2.3 sigma, below the threshold for confident claims. The signal is there in the data. It is not definitive. What elevates LHS 1140b above other candidates is not just the atmospheric hint. It is the host star. LHS 1140 is remarkably quiet. Unlike Proxima Centauri with its catastrophic superflares, unlike TRAPPIST-1 with its 4 dozen flares per observing period, unlike Kepler 438 with its monthly surface sterilizing events, LHS 1140 shows minimal flare activity. The star is relatively old and has settled into a stable middle age. Its ultraviolet and X-ray output are modest compared to other red dwarfs. This matters enormously. A planet cannot maintain an atmosphere if its star keeps blowing that atmosphere away. The quiet nature of LHS 1140 means that any atmosphere on LHS 1140b has a fighting chance of surviving over geological timescales. The research team that analyzed the JWST data described LHS 1140b as perhaps the best habitable zone exoplanet currently suited for atmospheric characterization. That is careful scientific language, but it carries real weight. After years of disappointing results from promising candidates, here is a planet where the star is not actively trying to murder any potential biosphere. LHS 140b is probably tidally locked like all close-in planets around red dwarfs. One side faces the star constantly, while the other faces away into eternal darkness. But if the planet has a dense enough atmosphere, heat could be redistributed effectively between the hemispheres through atmospheric circulation. Winds would carry warmth from the bright side to the dark side. And if there is a global ocean beneath that atmosphere, the geometry becomes even more interesting. The permanent day side might feature a large zone of open water, kept liquid by constant stellar radiation. The night side would be frozen. Life, if it exists, might be concentrated in the twilight zone, where liquid water meets ice. This is not proof of habitability. It is not confirmation of an Earth twin. LHS 1140 Key is larger and more massive than Earth, orbits a red dwarf instead of a sun-like star, and may be more ocean than land, but it represents our best current opportunity to study a rocky world in the habitable zone, with possible evidence of a secondary atmosphere around a star stable enough to permit long-term conditions compatible with life. If we are going to find signs of life on an exoplanet in our lifetime, LHS 1140b is currently one of the best places to look. Let me explain why this planet has emerged as the leading candidate, because the story illustrates how our understanding evolves as data improves. When LHS 1140b was first discovered in 2017, the initial mass and radius measurements suggested it could be either a rocky super-Earth or a small water world. The uncertainty was significant enough that researchers could not confidently classify it. Some models fit the data with a planet like a scaled-up Earth, with a large iron core and a rocky mantle. Other models fit equally well with a planet that had a much smaller iron core and a significant water layer. This ambiguity persisted for years because the measurements were not precise enough to distinguish between compositions. The planet clearly was not a mini Neptune with a thick hydrogen envelope, but whether it was rock or rock, plus water remained uncertain. The JWST observations changed that. By measuring the thermal emission from the planet during secondary eclipse, when the planet passes behind its star, astronomers could constrain the planet's temperature profile and reflectivity with unprecedented precision. Combined with improved mass measurements from radial velocity observations, the new data tightened the constraints on bulk composition. The mini-Neptune scenario was ruled out at 10 sigma. The planet does not have a primordial hydrogen envelope. It is either a bare rock with an atmosphere, or it is a water world with an atmosphere, or possibly a bare rock without an atmosphere. The latter scenario seems unlikely given the tentative nitrogen detection, but more data is needed. If LHS 1140b is a water world, it would be unlike anything in our solar system. Earth is 0.02% water by mass. Even if you drained all the oceans and melted all the ice caps, water would be a tiny fraction of Earth's total mass. LHS 1140b might be 10 to 20% water. That is an ocean hundreds of kilometers deep, perhaps with exotic, high-pressure ice phases at the bottom that do not exist anywhere on Earth. Such a water world would have no continents, no islands, no land at all. The entire surface would be ocean, possibly with an ice layer on the permanent night side. Life, if it exists, would be entirely aquatic. There would be no place for land plants, no forests, no grasslands, just endless water under an alien sky. This is very different from our picture of Earth-like, which usually involves continents and beaches and tide pools and all the ecosystems that depend on the interface between land and sea. A water world might be habitable in the sense that liquid water exists and life could evolve, but it would be a radically different form of habitable. The tentative nitrogen detection adds another layer. If confirmed, it would mean LHS 1140b has a secondary atmosphere generated by geological processes rather than a remnant of planetary formation. This is exactly the kind of atmosphere Earth has. Our primordial hydrogen and helium escaped billions of years ago. What we breathe today came from volcanoes, comet impacts, and biological activity over geological time. Nitrogen is stable. It does not react easily with other elements. It does not get stripped away by stellar radiation as readily as hydrogen. A nitrogen atmosphere on LHS 1140b could persist for billions of years, providing a stable environment where complex chemistry could unfold. The combination of a nitrogen atmosphere, possible surface water, and a quiet host star makes LHS 1140 genuinely exciting. After so many candidates that fell apart under scrutiny, here is one that keeps looking better as we learn more. But I must temper expectations. The nitrogen detection is at 2.3 sigma, which means there is still a several % chance it is noise. The water world scenario is one interpretation of the data, not a confirmed fact. We do not know if any atmosphere exists beyond the tentative hints. We do not know if liquid water exists on the surface. We certainly do not know if life exists. LHS 1140b is a promising candidate. It is not a confirmed habitable world. The distinction matters. I want to step back now and talk about what we have learned from all of this, because the story is not really about individual planets. It is about the refinement of a question. When the search for exoplanets began in earnest in the 1990s, the question seemed simple. Are there other Earths out there? The assumption, implicit in science fiction and explicit in some scientific speculation, was that the universe might be full of planets just like ours, rocky worlds with liquid water oceans and oxygen-rich atmospheres, worlds with forests and fish, and maybe even thinking beings looking back at us through their own telescopes. What we have learned is that the question was too simple. There are rocky planets in habitable zones. We have confirmed dozens of them. Statistical extrapolation suggests there might be tens of billions in our galaxy alone, but almost none match Earth in detail. The ones orbiting sun-like stars are hundreds or thousands of light years away, too distant for detailed atmospheric study with current technology. The ones close enough to study orbit red dwarf stars with flare activity and tidal locking and billion-year cooking phases that may have sterilized them before complex life could evolve. The Earth Similarity Index captures some parameters, but misses others that turn out to be crucial. A planet can score 0.88 on ESI and be bathed in sterilizing radiation every few months. A planet can sit perfectly in the habitable zone and have no atmosphere because its star stripped it away eons ago. A planet can look Earth-like on paper and turn out to be a mini Neptune with no solid surface, or a water world with oceans too deep for our concepts of habitability to apply. We have also learned that our detection methods create biases that shape what we find. Transit photometry discovers planets with short orbital periods around small stars because those produce the deepest, most frequent transit signals. Radial velocity discovers massive planets on close orbits because those produce the strongest stellar wobbles. Earth-like planets on Earth-like orbits around Sun-like stars are at the very edge of what we can detect, and we struggle to confirm them even when we find plausible candidates. The most Earth-like planet we have ever found might not be very Earth-like at all. By any strict definition, LHS 1140b is larger and more massive than Earth, orbits a red dwarf instead of a Sun-like star, is probably tidally locked with one face in eternal day and the other in eternal night, and might be an ocean world with no continents rather than a continental world with oceans. TRAPPIST 1e is smaller and less massive than Earth, orbits an ancient red dwarf, is certainly tidally locked, and shows no confirmed atmosphere, despite being the most studied, potentially habitable exoplanet. Proxima Centauri. B has roughly Earth's mass, but orbits a flare star bathing it in lethal radiation on a regular basis. None of these are Earth's twin. They are Earth's distant cousins, at best, worlds that share some characteristics with our planet, but differ in ways that might make them utterly alien or utterly dead. This brings me to a deeper question that the search for Earth-like planets inevitably raises. What does Earth-like even mean? And is finding Earth's twin really what we should be looking for? When we say Earth-like, we usually mean a planet that resembles Earth in the parameters we can measure. Similar size, similar mass, similar surface temperature, located in the habitable zone of its star. These are the criteria we use because they are the things we can detect from light years away using current technology. But Earth-like in this technical sense might not mean Earth-like in any meaningful sense for life. Consider that Earth itself has not always been Earth-like by our current standards. For the first 2 billion years of Earth's existence, there was no oxygen in the atmosphere. Cyanobacteria had not yet evolved to produce it through photosynthesis. If we had observed early Earth from a distant star, we would have seen a world with an atmosphere of nitrogen, carbon dioxide, and methane. We would not have detected the oxygen that we now consider essential for complex life. Early Earth would have failed our biosignature tests. Even after oxygen appeared, Earth went through periods that would seem utterly inhospitable. The snowball Earth episodes around 700 million years ago covered the entire planet in ice for millions of years. Average global temperatures dropped to -50 degrees Celsius. If we had observed Earth during a snowball phase, we would have seen an ice world that looks nothing like the blue marble we know today. And Earth's future is not guaranteed to remain Earth-like either. As the sun gradually brightens over billions of years, Earth will eventually become too hot for liquid water. The oceans will evaporate. A runaway greenhouse effect will turn Earth into something resembling Venus. In about 1 billion years, complex life will become impossible. In about 4 billion years, the sun will expand into a red giant and potentially engulf Earth entirely. Earth-like is a snapshot, not an eternal state. Our planet is Earth-like now, in this particular slice of time. It was not Earth-like before, and it will not be Earth-like forever. This should make us humble about what we can learn from remote observations. When we observe an exoplanet, we see it as it is at one moment in its billions of years' history. We cannot know if it was habitable in the past or will be habitable in the future. We can only ask if it appears potentially habitable now. It should also make us thoughtful about what we are really searching for. Are we looking for Earth's twin, a planet that happens to resemble our own at this moment? Or are we looking for places where life might exist, which could include worlds very different from Earth? Some scientists argue that we should expand our search beyond Earth-like planets. Perhaps life could exist in the subsurface oceans of icy moons, like Europa or Enceladus in our own solar system. Perhaps life could exist in the thick atmospheres of sub-Neptune worlds, floating in clouds of hydrogen and water vapor. Perhaps life could exist in forms so different from Earth life that we would not recognize it as life at all. The focus on Earth-like planets is partly pragmatic. We know life exists on Earth, so we know Earth-like conditions can support life. We do not know if life can exist under radically different conditions, so searching for those conditions is more speculative. But it is also partly a failure of imagination. We search for what we know because we do not know how to search for what we do not know. For now, Earth-like remains our best guide, and the search for Earth-like planets, despite its limitations and disappointments, has taught us something profound about our place in the universe. The James Webb Space Telescope has been operating for about 3 years as of early 2026, and its impact on exoplanet science has been profound. But perhaps its most important contribution has been revealing what we do not know and cannot easily learn. JWST was designed primarily for deep field cosmology and the study of early galaxies. Its exoplanet capabilities are extraordinary compared to any previous telescope, but they are still limited. It can characterize the atmospheres of large planets and planets around small stars, where the signals are strongest. It struggles with Earth-sized planets around Sun-like stars because the signals are simply too faint. The TRAPPIST-1 observations illustrate this limitation. After hundreds of hours of observation, time spread across multiple planets, we have ruled out thick atmospheres on the inner planets, but cannot confirm or deny thin atmospheres. We have possible hints for TRAPPIST-1e, but nothing conclusive. The habitable zone planets remain question marks after years of the most intense study ever directed at an exoplanetary system. The K2-18b observations showed that even when JWST detects atmospheric molecules clearly, interpretation is challenging. Is the methane biological or geological? Is the DMS real or noise? Is the planet a water world or a mini Neptune? The data are consistent with multiple interpretations, and distinguishing between them requires more observations, better models, and probably instruments that have not yet been built. LHS 1140b offers perhaps the best atmospheric characterization opportunity among potentially habitable planets, but even there, the nitrogen detection is only at 2.3 sigma. More observations might strengthen the signal, or they might reveal it was a mirage, an artifact of noise or stellar contamination. The fundamental problem is that we are trying to detect spectral features at the parts per million level in a light that has traveled tens or hundreds of light years. The signal we seek is buried in noise from the detector, from the instrument, from the telescope itself, and from the star. Stellar activity contaminates the spectra with features that can mimic atmospheric absorption. Instrumental systematics create artifacts that look like real signals until you analyze them more carefully. Even when real signals exist, distinguishing them from artifacts requires careful analysis and independent replication. The history of exoplanet atmospheric detections is littered with claims that did not hold up under scrutiny. Early reports of water on exoplanets sometimes turned out to be instrumental effects. Claims of exotic atmospheric compositions were revised or retracted as better data arrived. JWST has advanced the field enormously. It has given us the first real atmospheric spectra of rocky planets. It has ruled out certain compositions and confirmed others. It has transformed speculation into constrained possibility. But it has not solved the mystery of whether any exoplanet is truly habitable. It has sharpened the question and provided better data to narrow the range of possibilities. The answers, if they come, will require more observations with JWST, better instruments on ground-based telescopes, and probably space telescopes that have not yet been designed. The future of exoplanet science lies in missions designed specifically for the task we are now struggling to accomplish. The Plato mission, led by the European Space Agency and scheduled to launch in late 2026, will be the first space telescope designed explicitly to find Earth twins around Sun-like stars. Its array of cameras will monitor over 200,000 stars with enough precision to detect Earth-sized planets in year-long orbits. If there are true Earth analogues in the solar neighborhood within a few hundred light years, Plato should find them. But finding them is only the first step. Characterizing their atmospheres requires different capabilities. The Nancy Grace Roman Space Telescope, planned for launch in 2027, will use gravitational microlensing to detect planets at wide orbital separations, filling a gap in our current planetary census. Its coronagraph, a device that blocks the star's light to reveal faint nearby objects, will attempt direct imaging of giant planets around nearby stars. This technology demonstration will pave the way for future missions that can image smaller, fainter worlds. The ESO Extremely Large Telescope, currently under construction in Chile and expected to see first light around 2028, will have a primary mirror 39 meters in diameter, 4 times the size of any existing optical telescope. Simulations suggest it could detect biosignature gases in the atmosphere of Proxima Centauri b with about 10 hours of observation time. But this assumes there is an atmosphere to detect, which current evidence suggests is unlikely. The ultimate goal, the mission that could finally answer the question we have been asking since 51 Pegasi b, is the Habitable Worlds Observatory. This NASA flagship mission, currently in early planning stages for the 2040s, would be designed from the start to directly image Earth-like planets around Sun-like stars and analyze their atmospheres for biosignatures. The goal is to characterize at least 25 potentially habitable worlds, looking for the chemical fingerprints of life. If that mission succeeds, if we can point a telescope at a rocky world in the habitable zone of a sun-like star and detect oxygen, methane, water vapor, and nitrous oxide in its atmosphere, we will have achieved something unprecedented. Not proof of life, necessarily. All those molecules can be produced by geological processes under certain conditions, but a combination that strongly suggests biological activity, a world that looks, chemically speaking, like our own. Such a detection would not tell us what kind of life exists there. It would not tell us if that life is microbial or complex, simple or intelligent. It would not even tell us with certainty that life exists at all, because we might be missing some geological process that can mimic the biosignature. But it would narrow the question dramatically. Instead of asking whether habitable planets exist, we would be asking what lives on them. That day might come in the 2040s or 2050s, or the telescopes might reveal that such worlds are vanishingly rare. Perhaps every potentially habitable planet gets sterilized by stellar flares, or loses its atmosphere to the solar wind, or develops Venus-like runaway greenhouse effects. Perhaps Earth-like conditions are so rare that we are effectively alone in the observable universe. Both outcomes would be profound. Finding biosignatures would tell us that life is common, that the universe tends to produce it given the right conditions. Finding nothing but dead worlds would tell us that Earth is extraordinarily special, that the chain of events that led to life here was almost impossibly unlikely. Either way, we would learn something fundamental about our place in the cosmos. That is the true value of this search, not the discovery of a particular planet that we might someday colonize, because we will never colonize any of these worlds. The distances are simply too vast. The value is in understanding whether life is an expected outcome of planetary chemistry or an extraordinary accident. The search for another Earth is really a search for understanding ourselves. Are we cosmic commonplace or cosmic miracle? Is life an inevitable consequence of stars and planets and time? Or is it a one in a trillion fluke? These questions have occupied philosophers and theologians for millennia. For the first time in human history, we have the tools to answer them scientifically. Let me close with some perspective on what we have accomplished and what remains unknown. In 3 decades of exoplanet science, we have transformed our understanding of planetary systems. Before 1995, we knew of exactly one planetary system, our own. We had no idea if the Sun's retinue of worlds was typical, unusual, or unique. Some scientists speculated that planetary systems might be rare, that the conditions required to form planets might be narrow. Others assumed planets must be common based on theoretical arguments about how stars form from rotating disks of gas and dust. We had no data. We had speculation and hope and mathematical models, but no observations of planets around other stars. The discovery of 51 Pegasi b changed everything. It proved that detection was possible, that the signals were within reach of existing technology, that the universe had not hidden its planets beyond our ability to find them. What followed was an explosion of discovery. Ground-based radial velocity surveys found hot Jupiters by the dozen. The Kepler mission revealed thousands of planets through transit photometry. TESS continued the survey around brighter, closer stars. Ground-based direct imaging captured a handful of massive planets at wide orbital separations. Gravitational microlensing detected planets around distant stars that we will never observe again. The diversity exceeded all expectations. We found planets orbiting their stars in days and planets orbiting in centuries. We found planets larger than Jupiter and smaller than Earth. We found planets around binary stars and planets apparently ejected from their birth systems, wandering alone through interstellar space. We found systems with planets packed like sardines, orbits so tight they would be unstable in our solar system, but somehow persist for billions of years. we found systems with single lonely giants, systems with eccentric orbits that would scramble any inner rocky planets, systems that look nothing like our own. And amid all this diversity, we found planets in habitable zones, planets the right size, planets with the right temperatures, at least on paper, candidates for Earth's twin. They orbit sun-like stars and red dwarfs and binary systems. They range from smaller than Mercury to larger than Jupiter. They exist at distances from their stars ranging from a few stellar radii to hundreds of astronomical units. Some have circular orbits like Earth. Others have elliptical orbits that carry them through wild temperature swings. We know that rocky planets in habitable zones are common. The Kepler mission estimated that there might be 40 billion Earth-sized planets in habitable zones in our galaxy alone. Even if only a tiny fraction are truly habitable, the numbers are staggering. Hundreds of millions of potentially habitable worlds in this one galaxy. And there are 2 trillion galaxies in the observable universe. But common does not mean identical to Earth, and potentially habitable does not mean inhabited. We have found worlds that seemed perfect until we looked closer. Kepler 452b might not exist. Kepler 438b gets fried by stellar flares. TRAPPIST. One's inner planets are bare rock. Proxima Centauri b orbits a star that produces lethal superflares. K2-18b's biosignature is probably noise. The most Earth-like planet we have ever found, by my assessment, is LHS 1140b. Not because it is a perfect match for Earth, but because it represents our best current opportunity to study a rocky world in the habitable zone with possible evidence of an atmosphere around a star stable enough to permit long-term habitability. It is 49 light-years away, close enough for detailed follow-up observations. It transits its star, allowing atmospheric characterization through transmission spectroscopy. And that star, unlike most red dwarfs, is not actively trying to strip away any atmosphere that might exist. But LHS 1140b is not Earth's twin. It is a super-Earth, probably tidally locked, possibly covered in a global ocean kilometers deep. If life exists there, it would be profoundly different from life on Earth. Creatures adapted to eternal twilight zones between scorching day and frozen night. Organisms swimming in oceans under alien skies. Chemistry and biology that evolved under conditions no Earth life has ever experienced. And if no life exists there, LHS 1140b will still teach us something vital about the conditions required for biology. Every planet we study, habitable or not, adds to our understanding of what makes Earth special. The data accumulate, the models improve, the questions sharpen. We are not at the end of this story. We are still in the early chapters. The James Webb Space Telescope has given us our first real glimpse of exoplanet atmospheres, but the picture remains blurry and ambiguous. The missions of the 2030s and 2040s will sharpen that picture dramatically. Somewhere out there, among the hundreds of billions of stars in our galaxy and the trillions of galaxies in the observable universe, there might be another Earth, a world with blue oceans and green continents and the white clouds swirling over a pale atmosphere, a world where something looks up at the night sky and wonders if anyone else is out there. We have not found that world yet. We may never find it in our lifetimes. The distances are too vast, the signals too faint, the challenges too great. But we have found something remarkable anyway. We have found that the universe is full of worlds, not just hot Jupiters and barren rocks, but planets in habitable zones, planets with atmospheres, planets with water. The question is no longer whether other Earths could exist. Physics and statistics tell us they almost certainly do. The question is which of the candidates we have found might actually support life. That is a question we are getting closer to answering. Not today, not tomorrow, but perhaps within the next few decades. The telescopes are being built, the observations are being planned, the data are slowly, painstakingly accumulating, and somewhere, 49 light-years away, a planet called LHS 1140b circles its quiet red star, cloaked perhaps in a nitrogen atmosphere, harboring perhaps a global ocean beneath alien skies. We are watching, we are listening, we are learning. The search for another Earth continues.